So if I were to solve part A, I'll go ahead and write my current here is 20 amps. My length vector is the total length, which is 1.0 meters. And this is pointing in the I hat direction, because the length vector is pointing in the same direction as the current. So this is 1.0 meters, but pointing in the I hat direction. Then my magnetic field vector B is 0.5 Teslas. Can someone tell me what the direction of that magnetic field is?
Negative K.
It's negative K. Okay, so now let's go ahead and calculate what the force should be. So the force should be, so if you just multiply everything out, this should give you, so 20 times 1 times 0.5, so this should be 10. And if your current is in amps, your length is in meters, your magnetic field is in Teslas, then your force is going to be in newtons. So we can say that this is equal to 10 Newton. That's the magnitude. And then for the direction, we take I cross negative K hat. All right. So we know that K hat cross I hat is J hat. So I hat cross K hat is negative J hat, and the negative will cancel. So convince yourself that this is going to be equal to 10 Newton in the J hat direction. Does everyone agree with that? So that magnetic field is going to be pushing that wire to go up. The force is pointing up. So you're pushing it up. Now, let's do part B. For part B, the current is the same. So remember that the current, I keep the magnitude. So again, this is still 20.0 amps. But then the length vector here, the magnitude is the same. So this would be in the negative I hat direction. The magnetic field is the same, 0.5 Teslas in the negative K hat direction. Now put everything together here and do the math correctly. You should just get negative 10 Newton. So this is just to tell you that by changing the direction of the current, by changing the magnetic field, I can change the force, right? Is the force going to be pointing up or down? It just depends on the direction of the current. Any questions about this? Okay, so let's go back to this. So keep this, I think this is a very, very useful equation that you want to make sure that you know how to use it. So let me go back to my PowerPoint. Let's go back to the PowerPoint slide. Share this. Okay. Now, what you see here is just a different way to derive the same equation here. So if you remember this equation that we just... A second way that you can derive this equation is to start with the force on just one charge. And then you want to calculate how much amount of charge do we have in a given volume. So if you think about this conductor here, so this is my conductor, I can say that the volume, so V stands for the volume. So the volume is given by the length of the conductor times the cross-sectional area. Then I can calculate how much amount of charge is in that volume by taking N. Again, remember N from, so N is the number of electrons. A cubic meter. So if you remember in exam number 2, we use this equation here to calculate the drip velocity. So if you want to calculate the drip velocity, you need to know what n is, right? So again, n is that number of electrons per cubic meter that you can calculate if you know what the Avogadro's number is, and if you know what the density of the conductor is. So I think there was one equation that showed you exactly how to do that. So if this is the volume, and if this is the number of electrons per unit volume, so if you multiply these two together, it gives you the total. So all of this is the total number of electrons. And so if this is the force on one charge, you just want to multiply by this to get the total force. So force on one charge times the total number of charges that I have in the system. Then you can rewrite this equation here. So there's two ways that you can write this equation. For example, you can write this equation as L, I plus B. Or you can also write it as I, L plus B is the same thing. So if you want to use this, you're going to say that, okay, you want to focus on the current vector. But if you want to use the second equation, you can say that, well, take the current as a constant and then instead use the length vector. But the point is that the length vector and the current vector are pointing in the same. So the direction is the same. So we're just going to use this equation here. So we treat the current as a magnitude and then just focus on using the length vector. All right, so let's look at this example here. Now, something that I want to mention here is that if you look at this problem here, you can see that it gives you what the direction of the current is. In the exam, I might not give you the direction of the current, but you should be able to determine the direction of the current just by looking at this body right here. So if this is your body and this is your plus and minus, then we know that the direction of the current is such that the current always goes from plus to the high potential to the low, right? So the very first thing is that you want to get the direction of the current, and then you set up the system. So this is a problem where you need to be able to set up. So if you look at this current here, the first thing is that you want to notice that your magnetic field is pointing like that. So magnetic field always goes from the north to the south. So it means that your magnetic field can be written in this form here is the magnitude times J hat direction. So we're using a system where, so this is my I hat. And this is my J hat. And then my K hat. So again, let me try to see if I can. So I'm using a coordinate system that looks like this, right? This is my, so remember we're talking about 3 coordinates here. So everything here is on the XY plane, so X and Y. But you also have the K direction that makes 90 degrees with respect to this surface right here. So if this is my I direction, this is I, and this is my J, then my K is pointing up, right? Because again, remember that positive is always going in the counterclockwise direction. So for example, if this is my I and this is my J, it means that I cross J is K, and K is pointing up. Then J cross K will be I, which I is pointing like out of the screen like this. So again, just a little bit of, you need to just know exactly how to set up your coordinate system. So in this example here, your current is pointing in the I direction, and Then your J direction is pointing to the right, and your K direction is pointing up. All right. So if you think about, so the way I've drawn this, you can think about all of this here. So this circuit is, so that's like a sheet of paper. Then this would be the I hat, and this would be the J hat, and then the K hat makes 90 degrees with respect to that surface. So you set up everything. Again, the length vector is given by that. Because the length vector is pointing in the I hat direction, the magnitude of the current is just 20.0 amps. The strength of the magnetic field is given by that. So again, using this equation, you end up with that. So in this case here, the force is pointing, so the force is pointing up. Which again, if you know how to use the right-hand rule, so the right-hand rule, your thumb is pointing in the direction of the current, and then the rest of your fingers are pointing in the direction of the magnetic field here. All right. Then so when you have an open palm, so if you're an open palm means that the force is up. A closed palm means that the force is down, right? So in that case, you can write this equation here as I. Now, you can use this equation to calculate the magnitude of the force, and then use the right-hand rule to get the direction. Now, notice that writing this equation here, theta is the angle between the current and the magnetic field, which in this case, theta is equal to 90 degrees. So if theta is equal to 90 degrees, it means that the magnitude of the force is just the current times the length times the magnitude of the magnetic field. But I think the best way to solve it is to set up, like the way that I prefer to solve it is to get your directions, and then you calculate the force using this equation. Because once you calculate the force using this equation, it comes with the magnitude as well as the direction.